Hello everyone and welcome to today's lecture on microstrip antenna. In the last lecture we talked about microstrip antenna, just a very simple rectangular microstrip antenna configuration. Then we looked into what are the advantages and disadvantages of microstrip antenna, and based on its several advantages there are too many applications. In fact, today microstrip antennas are replacing majority of the conventional antennas. Now, because of these several advantages it is finding these application. Of course, there are some disadvantages we looked into in the previous lecture, but slowly and steadily many of those disadvantages are also being taken care of. And then we also looked into what are the different feed techniques. So, for example, a microstrip antenna can be fed by a coaxial line, it can be fed through a microstrip line, it can be aperture coupled or it can be electromagnetically coupled. So, today we will look into how to design very simply and in a quick manner a rectangular microstrip antenna. So, let us just see a basic rectangular microstrip antenna. A basic rectangular microstrip antenna is defined by its length L and its width W, and what we have here is we have a substrate. Okay. So, it is on one side of the substrate there will be a ground plane. So, that means copper will remain as it is in the back side, and on the front side we cut this or etch this patch of length L and W. So, now we need to design antenna for a given frequency, but before we do design let us just look at what are the parameters and what are the things there. So, first of all, if we have a patch here, so that patch will have a fringing field, just like think about this as a one plate metallic plate and one metallic plate is on the back side. So, there will be fringing fields all around. So, the total capacitance will be the capacitance of the parallel plate plus the capacitance of the fringing field. So, what is done actually, that to account for those capacitances because of the fringing field, we define the quantity L effective and W effective. So, L effective is nothing but total length L plus this delta L that accounts for the fringing field on one side and delta L on the other side. So, LE becomes L plus 2 delta L. Similarly, we define WE, which is W plus delta W and delta W, that becomes 2 delta W. Now, the next part is how do we calculate delta L. Now, there are several expressions available in the literature and they are fairly complicated expressions available, and these expressions have been derived by writing boundary conditions for electric field, magnetic field, solving all those Maxwell's equation, but that takes lot of time. And what we would like to do in the real life, especially the practicing engineers, they would like to design antenna quickly. So, what we have proposed here is a very simple expression to calculate delta E, and that can be calculated from the height of the substrate, or sometimes we call it thickness of the substrate divided by square root epsilon E. So, then comes the next part, what is the resonance frequency of this particular antenna. Now, the resonance frequency of the antenna is defined by the expression which is given over here. In reality it is relatively simple thing. I will just explain first for the fundamental mode. A fundamental mode is nothing but 1-0 mode. I will explain one by one. So, if we take fundamental 1-0 mode, so that means M is equal to 1 and N equal to 0. So, if this is 0, this term will not exist, and M by L is 1 by L square and there is a square root. So, L will come out here, and in reality if you actually see, this is nothing but when L becomes roughly equal to lambda by 2, that is what will be the resonance frequency for the fundamental mode. We will see one by one what are the different modes, but let us start the discussion for fundamental mode. So, we put M equal to 1 and N equal to 0, and what does this fundamental mode really imply? So, if it is 1, then this length L is equal to lambda by 2, and what does lambda by 2 really mean? That, see, we have for current, let us just look from the current point of view. So, we have an open here and we have an open here on this side. So, along the open current will be 0. So, since the length is lambda by 2, so current will be 0, it will go to the maximum, it will come back to 0, that is what is a half wavelength, and that is what the variation is known as 1. since we are talking about n equal to 0, what n equal to 0 means that along this axis there is no variation. So, that means if the current is 0 here, maximum here, 0 here, then current is 0 here, maximum here and 0 here. Now, since effective length is slightly more than the physical length, so in reality current is absolutely 0 here, goes to maxima and then comes back to 0 here. Now, voltage distribution will be reverse of that. So, open circuit means voltage will be maximum and then it will go to 0 and then it will come back to the minus this thing. So, plus 0 minus. So, what it really is, again this is nothing but equal to lambda by 2 length, which is a variation of the waveform. Now, since voltage is maximum here, current is close to 0, well here it will not be exactly 0, here it is 0, but this one we do not see, we only see the physical dimension. So, but nevertheless current is small, voltage is maximum. So, V by I, which is impedance, impedance will be maximum. At the center voltage will be 0, current will be maximum. So, impedance will be V by I, so impedance will be 0. So, along this length here, either you think this length or along the center or along the top, the impedance will be 0 here, it will be maximum. So, we feed at the center point here, basically it is known as a symmetrical feed. So, if we feed in the center here, so then this is 0 impedance and at the edge it is a maximum impedance. So, between 0 impedance and maximum impedance, we want to find a point where impedance will be equal to 50 ohm, because coaxial feed which we are using, those will be coaxial line or connector which are 50 ohm line or 50 ohm connector. So, our next problem would be is to find out the value of x, so that we can get a good match. So, now let us just see systematically one by one how is the field distribution going on. So, along the length we will just start from here. So, I have already told you that the at the end current is 0. So, that is a maximum and then current is 0. Along this here voltage is maximum and then voltage is becoming 0 over here. So, if we plot this voltage distribution along here, so voltage is maximum. So, the field will be going from here to here, this is the electric field, and then the field will be going here, and along the edges there will be fringing field, and this amplitude which is maximum here, and gradually it is reducing to 0. So, gradually it is reducing to 0 and then it changes the direction. So, now the arrow directions are there. So, now at this point if you see, so the field is going towards the patch which is a negative, and these are the fringing fields. So, now this whole thing can be represented in this particular form here, where what we are looking at, we are looking at two set here. One is the field beneath the patch. Now, the radiation takes place from the edges, because the field is confined within the patch here. So, now these fields here can be represented in two component, horizontal component and vertical component. So, horizontal component will be in the right hand side direction. So, this is where is the horizontal component. The vertical component will be going down, but from this side now if you see, the horizontal component is also in the right hand side, which is shown over here, and the vertical component will be in the opposite direction of this one here. So, if you look at a broadside direction, since these two are in the opposite phase, they cancel in the broadside. The only addition comes is from these two things which are in the same direction. So, this whole thing can be thought about as that there is a one radiating slot, there is another radiating slot, and now we need to find out what is the radiation pattern. So, in fact, we can apply the array theory. So, we can actually see that there is a one radiating slot on one edge, another radiating slot is on the other edge, and the distance between them is approximately lambda by 2. Why? Because that is what is the half wavelength corresponding to which is resonance frequency is there. So, now if we look into here then, so in order to find the radiation pattern, what do? We already know how to calculate the radiation pattern of a dipole antenna. Complement of a dipole antenna is slot antenna, and then we apply the array theory to find out the overall radiation pattern in this plane, and then these can be integrated along this axis to give the H plane pattern. Now, the simplified way of the analysis is also that we can think of this whole patch as a transmission line, and since the field is uniform, so we can neglect that particular part there. So, we assume that this is a simple transmission line. Fringing fields are represented by capacitance on both sides, and the radiation resistance is modeled over here. Now, how do we calculate radiation resistance? Well, we know that there will be electric field here. So, from the electric field we can find out what is the power radiated, and then power radiated is equal to V square by 2 R. So, from that we can find out the radiation resistance, and as I had mentioned earlier, this radiation resistance is not the physical quantity, it is just a representation of radiated power. So, now we can actually look at how to design the antenna. So, first of all, for the design what we need to calculate what is the effective dielectric constant. Why effective dielectric constant? Let us just go back and see the distribution. So, we can see that most of the field is confined in the substrate, but part of the field is going up in the air. So, because of that the effective dielectric constant is not really only epsilon r, but it is slightly less than epsilon r, because part of the fringing field is in the air. So, we can use this particular formula calculate what is epsilon effective. Now, again for this there are so many different expressions are given. This we found out is reasonably good expression which can be used for rectangular patch antenna. So, one can actually see that if W is going towards infinity, that means patch is very long, and if W is infinity, this term will be equal to 0, then this whole term becomes 1, and if you look into here, then this entire term becomes epsilon r. So, which is expected if the patch is spread to the infinity, epsilon effective will be equivalent to epsilon r. However, if the width is very small, if it is tending towards 0, if you put this expression, epsilon e will be nothing but equal to epsilon r plus 1 by 2. Why? Because epsilon r is below the patch and 1 is the above the patch. So, we need to take effective dielectric constant, but majority of the time for a rectangular patch we take a larger width. So, epsilon e is given by this particular expression, and where we can also say epsilon e is slightly less than epsilon r. Now, we can see that there is a W here and we need to calculate the value of W. Now, here again a starting point has been given, and this starting point can be used to calculate W, and where is this starting point coming into picture? Well, just think about C by F0 is nothing but lambda 0. Lambda 0 divided by 2, which is approximately half wavelength, and then this is being divided by the effective dielectric constant between the dielectric layer down below and 1 above there. Now, again this is just a starting point. Now, it does not mean always that you have to choose this value of W. You can take a larger value than this W or smaller value of W. It all depends upon, just to tell you right now, that if you take a larger value of W, then what will happen? Aperture area will increase. So, if aperture area increases, that means gain will increase. So, if you require a larger gain, you can take larger W. Also, if W increases, fringing fields will increase, and if fringing fields increase, that means there will be more radiation. From circuit point of view, that means there will be more losses, and more lossy means Q will be low, and if Q is low, bandwidth will be high. So, one can actually choose, but sometimes we may have to take a smaller than this W, because we need to fit the antenna into a certain area. Suppose let us say you want to design an antenna for a mobile phone, you can't use a very large W because of the size of the mobile phone is small. So, you may end up taking a small W, which will then compromise on the bandwidth as well as on the gain. And once we know W and epsilon, then we can actually find out the value of LE, which is effective length. Let us say LE should be equal to this here. What is this here? That is lambda by 2. And what is lambda? Lambda is nothing but lambda 0 divided by square root epsilon E. So, then this basically is nothing but lambda by 2, and that is what we had seen for fundamental mode. 1 0, the length should be equal to lambda by 2, and LE is nothing but L plus 2 delta L, and what is lambda 0 is C by F 0. So now let us say we want to do the design. So design, we need to use this equation. So let us say frequency is given to us. So for a given frequency, we can choose first W. So W will be used, F0 is known, epsilon r is known, because we have chosen a substrate, we can calculate W. For this given value of W, substitute over here, find out the value of epsilon e. Then this value of epsilon e we can put over here and find out what is the effective length, and then from that we can calculate the physical length. We will take a design example. However, we also need another thing, where should we feed. So in order to feed, I have given a general guideline, the feed point can be between L by 6 to L by 4. So if it is a narrow band antenna, start with L by 6, if it is a wide band antenna, start with L by 4. So let us just take a design example. So we will start with the design of a rectangular microstrip antenna for Wi-Fi application. You know that Wi-Fi works around 2.45 gigahertz, but the exact frequency ranges from 2.4 to 2.483. Now till now we have not really looked into what controls the bandwidth, what controls the gain and other thing. So what we will do, we will just take one of the standard substrate. So this is a substrate whose parameters are epsilon r 2.32, H is 0.16, which is really equal to 1 by 16 inches, and tan delta is 0.001, which is a low loss substrate. Now we know the frequency, so take the center frequency of this as 2.4415, which is in between center value. So our first task is to calculate W. So we know the parameter C, C is nothing but 3 into 10 to the power 8 meter per second, but here we have represented in terms of centimeter. So 3 into 10 to the power 10 centimeter per second. So here is the 2 which is coming here, F0 is 2.4415 into 10 to the power 9 gigahertz, and 2.32 plus 1, 3.32 divided by 2 is 1.66. So we do the calculation, it comes out to be 4.77 centimeter. Now as I mentioned, it is not necessary that you take this value of W, you can take any different value. So I have just taken a value which is 4.7, you can take 4 also, you can take 5 also, you can take 3 also, depending upon the requirement. For this value of W now, we substitute the value of epsilon r, which is 2.32, H is known 0.16, put W here, do the calculation, epsilon effective is 2.23. You can see that this 2.23 is slightly less than 2.32. Okay. So that tells that you are on the right path. If this is more than this, you know definitely it is not correct. So from here now, once we know this, we can find out L effective, we know C, we know F0, now we know epsilon E, substitute the value, we got 4.11 centimeter. And then the next part is to calculate L, which is a physical length. So we use this expression. Now delta L, as I mentioned, this is H by square root epsilon E, this is the approximate value, and that comes out to be 3.9 centimeter. But one thing I can assure you, if you just use these simple 3-4 lines, I can assure you that majority of the time your antenna will be designed within 1 to 2% of the accuracy. Absolute maximum error you take any case will not be more than 5%. In fact, most of the time we have found out the error is less than 1%. So let us just take an example here. So what we did, the same design now we have simulated using a commercially available software, which is IE3D. Earlier it was available from Zealand, now it is available from Mentor Graphics. So what we have done here, we took 3.9 centimeter, W4 as we calculated, X as 0.7. Now just recall I said starting point can be L by 6. Now 3.9 divided by 6 L is 0.65. I have taken slightly more than that, and there is a reason also. Here W is more than length, and if W is larger, that means bandwidth will be larger, that means impedance variation will be small. We will see the parametric study shortly also. So, because bandwidth is large, impedance variation will be relatively less. So, we have taken slightly more than 0.65. So, this is the 0.7. Epsilon r h tan delta, you have to specify these things in the simulation, and in the beginning we have done the simulation for infinite ground plane. Now, these are the results. This is the Smith chart plot, and that is a S11 plot. So, we can see here that what we have got here is a center frequency as 2.414, impedance is 50 ohm. So, this 50 ohm is reasonably close to 50 ohm. So, we can leave that here, and if you look at the S11, that is the S11 plot, but if you look for bandwidth for S11 less than minus 10 dB, you can actually just go through and draw a line at minus 10 dB, and one can see that the bandwidth obtained is about 40 megahertz. Now, this is really not our objective. Our objective was from 2.4 up to 2.483. So, we required 83 megahertz, but we have got only 40 megahertz. Do not be disappointed, because this is just the starting point. We just took some arbitrary substrate which has an epsilon r, and this and h is given by this value. We will see how to design a real antenna, but this is good starting point. But what we would like to show you here, that our designed frequency was 2.4415, which we took that, and simulated came out to be 2.414. So, if you calculate the percentage error, it is only about 1.1%, which is a very good thing. You do not have to solve Maxwell's equation, you do not have to write boundary conditions, you do not have to do E field, H field, double integral and so on. Just by using simple calculator you can do the design, and how much time it took, maybe less than 10 minutes. So, now the question comes, then what do we do next? So, we got a value which has a percentage error of 1.1%. So, what we simulated is 2.414. What was desired was this here. So, if we reduce the value of length L, so what will happen? Frequency will increase, and to increase the bandwidth, what we need to do? We need to increase H, so that bandwidth will increase. So, let us remember this starting point, okay. And now what we will do, we will study the parametric study. So, we will take a case one by one, we will see the performance of each and every parameter and see what really happens. So, as a starting and different design example, we have taken L equal to 3 centimeter and W equal to 4 centimeter, and these are the substrate parameters. And for the simulation, we have taken probe diameter as 0.12 centimeter. This is the diameter for SMA connector. There are two most popular connectors actually, one is a SMA connector, another one is a N type connector. So, we will show you the results one by one. Again, all these antennas have been analyzed using IE 3D software. So, let us see one by one effect of this. To start with, we have given effect of feed point location. So, what we have done, kept the L, W constant, epsilon r, h are also constant. All we are doing it is changing the value of x, and what we have taken x as 0.55, 0.6 and 0.65. Okay. These are the three values, and we can actually see the plot for x equal to 0.5. This is the impedance plot, and then this is for 0.6 and this is for 0.65. So, what we are effectively doing, by increasing the value of x, we are moving towards the edge of the rectangular microstrip antenna, and we know that at the center impedance is 0, towards the edge impedance is maximum. So, that is why when you are shifting the feed point towards the edge, impedance is increasing. Now, by changing the feed point location, resonance frequency does not change much. So, that is why you do not see much difference in the VSWR plot as far as the resonance frequency is concerned. However, one can see that the bandwidth is slightly different. If you draw a horizontal line for VSWR2 here, then we can see that the bandwidth for this solid line is slightly more than this here. So, how that can be explained? Again, let us just look at here. So, what we have these three impedance plot. So, what you need to do, you need to draw a line from this edge to this one cut here, and that is a chord. And then we see that the line which is going through the 50 ohm line, again that is a chord. but for this particular feed point, if you look at it, then what we can see that it is almost passing through the diameter of the VSWR equal to 2 circle, and that is where it is more important, and that is why this one gives a better bandwidth. So, in fact, I would like to tell my audience that it is not always important that you design antenna for exactly 50 ohm. In fact, most of the time when I design antenna for 55 ohm or 60 ohm impedance, which will be something like this plot here, and that will give me a slightly larger bandwidth. And here also let us look at the radiation pattern. Okay. Now, since it is simulator for infinite ground plane, so there is a no radiation in the back side, but what we have here, we have two things which are copolar. This is a E plane pattern and this is a H plane pattern. Okay. So, you can see that this E plane pattern, how does that E plane pattern comes into picture? So, you look at the slot antenna. So, slot antenna will have a omnidirectional pattern. So, let us say we have two slots here, there is an omnidirectional pattern here, omnidirectional pattern there, but below there is a ground plane. So, it will not radiate in the downside. So, the pattern will be something like this, pattern will be radiating in the upper hemisphere. Now, we apply the array theory, and the separation between the two is lambda by 2. This is not lambda 0 by 2 which we studied in array theory. So, compared to lambda 0 by 2, this is actually lambda 0 divided by 2 square root epsilon E. So, this length is still small. So, the radiation will be in the broadside direction, and that is why when we look at the pattern here, you can see that it is not exactly 0 because of the array factor, it is coming slightly less than that, but the main is in the broadside direction. What about this plane H plane? So, for H plane again you have to think about the slot antenna radiation. So, let us say this is the slot here, radiation is maximum around this. So, this is giving me E field, but H field is perpendicular to the E field. So, this side here, if you look at the slot, we see the maximum, but if we look from here, the radiation is actually equal to 0. So, that is why for H plane the radiation is starting from maxima, it is going towards 0 here. So, what is this component coming here? This is actually a cross polar component. Ideally, we would like there should be no cross polar component. A perfect linear polarized antenna should not have any cross polarization, but however, as one can see, the cross polar component is, this is 0, minus 10, minus 20, minus 30, that is about 27, 28 dB down compared to the maximum radiation in this direction. So, we can almost say cross polar is very less, but however, from where this cross polar is coming? Actually, this cross polar is coming, if you look at the patch, there is this probe here. So, from the bottom when we are feeding the patch, so what we see here, there is a ground plane and this probe is coming out, and then there is a patch. So, in fact, this probe can be thought about as a top loaded monopole antenna. So, basically this is a more like a monopole antenna. What is the radiation pattern of the monopole? Well, it will be 0 in this direction, maximum in this direction. So, if you actually look at this radiation pattern, so the cross polar is really speaking coming because of that monopole antenna or because of that probe which is radiating. Okay. So, if the probe length is more, the radiation will be more. In fact, we will see that the cross polar level component increases. So, this is the effect of the feed point location, and then we can also look at the next one, which is effect of the width. So, we can see here that results are given for different values of the width 2, 3, 4 and 5. So, this is the case for the width equal to 2, this is the for 3, this is for 4 and that is for 5. Okay. So, also there is a VSWR plot, this is for 2, 3, 4, 5. So, why we are getting this kind of a thing? Just think about, if the width is increasing, we saw the expression for epsilon I, larger is the width, epsilon effective will keep on increasing. So, if epsilon effective increases, resonance frequency will decrease. Also, if the width is large, fringing fields will also increase. And now coming to this here, So this can be explained as the width increases, there will be more and more fringing field, that means there will be more radiation. So more radiation means more losses, and that is radiation losses. From antenna point of view it is very good, but from circuit point of view we think it is losses, but that is not correct from antenna. More radiation is actually a desired quantity. So when there is a more radiation, so what will happen? Q will reduce, and that increases bandwidth, and if the bandwidth is increases, that means that the impedance variation will reduce. So impedance variation reduces means impedance will reduce. So that is why when we shift from W equal to 2 to 3 to 4 to 5, we can actually see that the impedance is changing, and one can choose a proper feed point for doing the impedance matching for any of these cases here. So we can actually note that bandwidth is proportional to W. So as you keep on increasing the value of W, we will see that the bandwidth increases, and gain is directly proportional to W, because W increases, aperture area increases, hence gain increases. So we will continue from here in the next lecture. So today we just looked into how to design a simple rectangular microstrip antenna for a different given frequency range. But in the next lecture we will first study what are the parameter effect of different components also for substrate parameter, and then we will see what determines the bandwidth of the antenna. Then we will take a real example to meet the exact requirement. So thank you very much, and we will see you soon.